Tonight, we're going to listen to something you have never heard before. Something that has been happening every single second of your life, every second of your parents' lives, every second of every human life that has ever existed on this planet, and yet something that no living creature has ever truly heard. 93 million miles away, a star is roaring. It has been roaring for 4.5 billion years. And tonight, I want to tell you what that roar actually sounds like, what it would do to you if the silence of space ever broke, and why the fact that you cannot hear it is perhaps the single greatest mercy the universe has ever granted us. Here is something most people never stop to consider. The sun is not a quiet thing. It is not the calm, steady light that warms your face on a summer afternoon. Beneath that golden surface, something violent and ancient is always happening. Plasma the size of continents rises and falls in churning columns. Magnetic fields twist and snap with the force of billions of nuclear weapons. Pressure waves roll through its interior like the deepest thunder you could ever imagine, bouncing from its core to its surface and back again in a rhythm that has never once stopped. The sun is shaking. It has always been shaking, and the sound it makes, translated into terms a human mind can hold, is almost too large to comprehend. By the end of tonight, you're going to understand exactly why scientists who first heard the sun's acoustic signature described it not with wonder, but with something closer to unease. You're going to understand what 290 decibels means, and why that number should change the way you think about the 8 minutes of silence between you and our star. You are going to understand why the universe is, in a very real sense, never quiet, and why the particular silence that wraps this small blue world is not emptiness at all. It is protection. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Step outside tonight, if you can. Step outside and look up at the sky, and find the place where the sun sat before darkness came. That patch of sky, that ordinary, unremarkable corner of the heavens, is where a star is screaming right now. It has been screaming since before this planet had oceans, since before this planet had a solid surface, since before any living thing drew a first breath on any shore anywhere on Earth. And you have never heard a single second of it. None of us have. And tonight, I want to sit with that fact for a while, because I think it is one of the strangest and most quietly terrifying truths in all of science. We talk about the sun the way we talk about a lamp, something that turns on in the morning and fades at night, something reliable, something familiar, something almost domestic in its constancy. But the sun is none of those things. The sun is a nuclear furnace 432,000 miles across. It is a churning, violently unstable ball of plasma so dense at its core that a single photon of light, born in a nuclear reaction in the very center, takes 100,000 years just to fight its way to the surface. Not to reach Earth, just to reach the surface. 100,000 years of bouncing, absorbing, re-emitting, and struggling through layers of plasma so thick they make our deepest oceans feel like a puddle. The sun is not calm. It has never been calm. And the sound it makes during that entire violent process is something the universe has, so far, kept entirely from us. Here is the thing most people do not realize. Silence and emptiness are not the same thing. When we say that space is silent, what we mean is that there is not enough matter between the stars for sound waves to travel the way they travel through air. Sound needs a medium. It needs molecules to compress and expand, to push against each other, to carry that wave of pressure from one point to the next. In the vacuum between planets, there are barely any molecules at all, so the wave cannot form, the sound cannot travel, but that does not mean the sound does not exist. Inside the sun, where plasma is packed at densities we can barely imagine, sound travels extraordinarily well. The sun is full of sound. It is overflowing with it. Pressure waves roll through its interior constantly, bouncing off internal boundaries, resonating through its layers like the inside of the most enormous instrument ever constructed. The silence you hear when you walk outside on a clear afternoon and tilt your face toward that warm light is not the sun being quiet. It is the universe keeping a secret. The first time scientists truly began to understand this secret was in the 1960s, though the discovery crept up on them slowly, the way all great discoveries tend to do. Researchers studying the surface of the sun, watching it through specialized telescopes, began to notice something strange. The surface was moving, not just in the turbulent, boiling way you might expect from a ball of superheated gas. It was moving rhythmically, pulsing, rising and falling in regular patterns that repeated with extraordinary precision every 5 minutes or so. The surface of the sun was oscillating like the skin of a drum, and once they understood what they were seeing, once they realized that these oscillations were pressure waves generated deep inside the star, they also realized something remarkable. They could use these waves to see inside the sun, the same way a doctor uses sound waves to see inside a human body. The field that was born from that realization has a name: helioseismology, and what it has revealed about the interior of our star over the past several decades is, in the truest sense of the word, astonishing. Think about what it means to hear a sound. When you hear a voice or a piece of music, or a door closing somewhere in a quiet house, what is actually happening is that something has disturbed the air, has compressed it and released it in a wave that travels outward in all directions, and some small portion of that wave reaches your ear, and your ear converts that pressure into a signal your brain interprets as sound. The distance between the source and your ear matters. The louder the original sound, the further it can travel and still be detected. So here is a question I want you to hold in your mind as we go through this together. If the sun is generating sound waves of almost unimaginable power inside its interior, and if those sound waves are powerful enough to make the entire surface of a star visibly rise and fall, how loud is the original source? How much energy is flowing through that plasma? And what would happen, what would actually physically happen if somehow that barrier of vacuum between us and the sun were removed and those waves could travel freely? The answer to that question is the heart of what I want to explore with you tonight. And I will tell you now, gently, because this is meant to be a peaceful journey through a terrifying subject. The answer involves a number, a specific number of decibels. And that number, when I give it to you in a little while, is going to change the way you think about the 8 minutes of travel time between the light leaving the sun and arriving on your skin. Because those 8 minutes, that 93 million miles of almost perfect nothing, is not just distance. It is the difference between a warm afternoon and something that the laws of physics suggest would be almost incompatible with the existence of matter as we know it. But we are not there yet. For now, I want you simply to hold the image. A star sitting 93 million miles away in the dark, its surface rising and falling in waves miles high, its interior crossed in every direction by pressure waves that have been travelling and bouncing and resonating for billions of years. A sound so enormous that our instruments can detect its effects from here, across the void, even though the void itself refuses to carry it. The sun is the loudest object in our solar system. It is possibly one of the loudest objects in this region of the galaxy. And every morning of your life, you have stood in its light without ever once hearing it. That is not a small thing. That is, when you sit with it quietly in the dark, one of the most profound silences there has ever been. Before we can truly understand what the sun is doing, before we can begin to grasp the scale of what is happening 93 million miles away every single second, we need to spend a little time with something deceptively simple. We need to talk about sound. Not in a technical way, not in the way a physics textbook would approach it, with equations and Greek letters and diagrams that make your eyes slide off the page. I want to talk about it the way you actually experience it, the way it lives in your body and your memory, because sound is not abstract, it is one of the most intimate things in the world. And once you understand what it truly is, what is actually happening when you hear anything at all, the story of the sun's voice will take on a weight it simply cannot have any other way. Close your eyes for a moment and think about a drum, a large drum, the kind you might see at the front of a parade, the kind that you feel in your chest before you properly hear it with your ears. When a hand or a mallet strikes the surface of that drum, the skin of the drum is pushed inward, suddenly and forcefully. That push compresses the air directly in front of it, squeezes the molecules of air closer together than they were a moment before. But air resists being compressed. Those molecules push back, spring outward, and in doing so, they compress the molecules next to them. And those molecules compress the next layer, and the next, and the next, in an outward moving wave of pressure that travels in all directions from that drum at roughly 767 miles per hour. That wave of pressure reaches your ear. Your eardrum, which is its own tiny membrane, vibrates in response. Tiny bones and fluid and hair cells translate that vibration into an electrical signal. And your brain, in a fraction of a second, converts that signal into the experience of a sound. That is all sound is. A wave of pressure moving through a medium, a disturbance, travelling outward from its source. The key word in everything I just said is medium. The wave of pressure needs something to travel through. In the case of the drum, it travels through air, but air is not the only medium sound can use. Sound travels through water, and it travels through water far better than it travels through air. The speed of sound in the ocean is roughly 3,355 miles per hour, more than 4 times faster than in air. Sound travels through solid rock even faster than that. Put your ear against a wall, and you can hear conversations that the air in the room would have muffled entirely. The denser and more elastic the medium, the better sound travels through it. This is not a small detail. This is everything when it comes to the sun. Because the interior of the sun is not air, it is not water, it is not rock, it is plasma, squeezed by its own gravity to densities that make the densest steel on Earth feel almost weightless by comparison. And in that plasma, sound does not just travel, it travels with a ferocity that is almost incomprehensible. Now think about volume, loudness. When we talk about how loud a sound is, we are really talking about how much pressure that wave is carrying. A whisper barely disturbs the air, a shout disturbs it more, a thunderclap disturbs it enormously. We measure this pressure in decibels, and the decibel scale works in a way that surprises most people when they first encounter it. It is not a linear scale, it is logarithmic. That means that every increase of 10 decibels does not add the same amount of energy, it multiplies it. 10 decibels more means 10 times the acoustic power. 20 decibels more means 100 times the acoustic power. 30 decibels more means 1,000 times. So when you hear that one sound is 30 decibels louder than another, the difference is not 30 units of something. The difference is a 1,000-fold multiplication of energy. The scale climbs steeply and fast, and the numbers at the top of it describe realities that are genuinely difficult to visualize. A quiet library sits at around 30 decibels. A normal conversation is roughly 60. A lawnmower running next to you is about 90. A jet engine at close range pushes past 140, which is also roughly the threshold at which sound stops being merely painful and starts causing immediate physical damage to the human ear. A large explosion, something like a conventional bomb detonating at close range, can reach 200 decibels. At around 210 decibels, something strange and significant happens. The sound wave becomes so powerful that the low-pressure phase of the wave, the part where the air expands back outward, can no longer pull the air pressure below zero, because there is no such thing as negative air pressure. At that point, the wave stops behaving like a normal sound wave and starts behaving more like a physical shock wave. The air itself begins to break down. The medium the sound is travelling through starts to be destroyed by the sound travelling through it. That is a threshold most people never think about, but it is important, because the number associated with the sun is considerably higher than that. Here is something else about sound that matters deeply for our story tonight. Sound carries energy, real physical energy. When that drum strikes and sends a pressure wave through the air, the wave is not just a signal, it is a transfer of energy from one place to another. Loud sounds carry more energy than quiet ones. That is why standing next to a speaker at a concert can leave your ears ringing for days, or why the shockwave from an explosion can shatter windows hundreds of feet away, or why certain very low-frequency sounds, infrasound, sounds below the range of human hearing, can cause nausea and disorientation, even when you cannot consciously detect them at all. The energy in the wave is real. It does things. It moves matter. And the more energy in the wave, the more dramatic the things it can do to whatever it passes through. I'm telling you all of this slowly and deliberately because I want you to have these ideas resting quietly in your mind when we turn them toward the sun. I want you to feel the drum, feel the wave, understand the medium, understand the scale. Because when we take everything you now know about pressure waves and energy and decibels and the behavior of sound at extreme intensities, and we apply it to a star that is 432,000 miles across and has been violently exploding in its own core every single moment for 4.5 billion years, the picture that emerges is not just impressive, it is something that sits right at the edge of what the word terrifying was invented to describe. And we are only just beginning. I want you to imagine something with me. Imagine a pot of water on a stove, just beginning to boil. You have seen this 1,000 times. The water at the bottom, closest to the heat, warms first. It becomes less dense than the cooler water above it. So it rises. It pushes up through the cooler water, reaches the surface, releases some of its heat into the air, cools down, becomes denser again, and sinks back to the bottom to be reheated. Over and over, in slow rolling cycles, this process has a name. It is called convection, and it is one of the most fundamental ways that heat moves through a fluid. Now take that image, that quietly bubbling pot of water, and scale it up. Scale it up by a factor so enormous that the numbers involved stop feeling like numbers and start feeling like something else entirely. Because what is happening inside the sun is convection. The same basic process. Except the fluid is not water, it is plasma heated to millions of degrees. And the bubbles are not the small lazy spheres you see in a pot on your kitchen stove. They are columns of superheated gas wider than the entire continent of North America, rising and falling at speeds of hundreds of miles per hour. The sun has layers, and understanding those layers matters for understanding the sound it makes. At the very center is the core, where the real violence happens. Temperatures there reach 15 million degrees Celsius. Under pressure, so extreme that hydrogen atoms are forced to fuse together into helium, releasing energy in the process. This is nuclear fusion, and it is the engine of the sun, the source of every photon of light that has ever touched your skin. Surrounding the core is a region called the radiative zone, where energy from the core moves outward, not by convection, but by being absorbed and re-emitted by plasma particles in a slow, staggering, random walk that, as I mentioned earlier, takes roughly 100,000 years to complete. And surrounding that is the convective zone, the outer third of the sun's interior, where the plasma finally becomes turbulent and convection takes over as the dominant mechanism of energy transport. This is where the shaking begins in earnest. This is where the sound is born. The convective zone is not a calm place. It is not a place of gradual, orderly movement. It is a seething, churning ocean of plasma in constant, violent motion, driven by the almost unimaginable heat rising from below and the relative coolness of the surface above. The cells of convection that form in this zone come in different sizes. The smallest visible ones, called granules, are roughly the size of Texas. They last for about 8 to 20 minutes before they dissolve and reform. At any given moment, the surface of the Sun is covered in approximately 2 million of these granules, each one a rising column of hot plasma surrounded by the cooler, sinking plasma at its edges, like a vast cobblestone surface made of fire. And above the granules, larger structures called supergranules span distances of up to 30,000 kilometers and persist for days. These are not gentle features. These are the visible signatures of an interior that is in continuous, powerful, never-ending turmoil. All of that motion generates pressure waves. It cannot do anything else. When you have fluid moving at high speeds, colliding with other fluid, moving in different directions, compressing and expanding in continuous cycles, you generate disturbances in pressure. You generate sound. The convective zone of the Sun is essentially an acoustic generator of staggering power, constantly pumping energy into pressure waves that travel through the solar interior in every direction. Some of these waves move through the outer layers of the Sun and dissipate quickly, but many of them travel deeper, into the radiative zone and toward the core, bouncing off internal boundaries where the density of the plasma changes abruptly, reflecting back toward the surface and then reflecting downward again. The Sun traps these waves. It holds them inside itself, letting them bounce back and forth, building up into resonant patterns the way sound builds up inside a concert hall or a cathedral. The Sun is, in the most literal physical sense, resonating. It is ringing. It is ringing like a bell that has been struck 4.5 billion years ago and has never been allowed to stop. The surface expression of all this internal motion is visible to the right instruments. And what those instruments show is extraordinary. The entire surface of the Sun is in motion, not just in isolated spots, everywhere. The surface rises and falls in oscillations with a dominant period of approximately 5 minutes. 5 minutes up, 5 minutes down, over and over, across the entire visible disk of the star. The amplitude of these oscillations, the distance the surface actually moves, is roughly 10 to 15 kilometers per cycle. That sounds almost modest until you remember that we are talking about the surface of a star. 15 kilometers of vertical movement across a surface millions of kilometers wide, happening in rhythmic waves driven by acoustic energy from the interior. If the Sun were the size of a basketball, these oscillations would be far too small for you to see or feel. But the Sun is not the size of a basketball, and the absolute energy contained in those oscillations is beyond anything our daily experience gives us the tools to intuitively grasp. Here is the thing most people do not realize about all of this motion. It is not random noise. It is not the acoustic equivalent of static on a radio. The pressure waves inside the Sun interfere with each other, combine and cancel in specific ways, and produce distinct resonant frequencies. Like the harmonics of a musical instrument, the Sun has a fundamental note, in a sense, and it has overtones, thousands of them. Researchers have identified and catalogued more than 10 million individual oscillation modes on the solar surface, 10 million distinct frequencies, all superimposed on each other, all carrying information about the interior of the star through which they have travelled. The Sun is not just making noise. The Sun is playing a chord of almost incomprehensible complexity, a chord that has been sustaining itself, uninterrupted, for longer than the Earth has existed. And we are only now, in the last few decades of human history, beginning to have instruments sensitive enough to listen. The year was 1962, and a solar physicist named Robert Layton was doing something that sounds almost mundane. He was taking photographs of the Sun. Specifically, he was photographing the Doppler shift of light coming from different parts of the solar surface, a technique that allowed him to measure whether parts of the surface were moving toward him or away from him at any given moment. It was painstaking work, the kind of observational science that requires patience and precision and a willingness to stare at data for a very long time before it tells you anything. And then, in the data, something appeared that was not supposed to be there. The surface of the sun was oscillating, moving up and down rhythmically, with a period of roughly 5 minutes. It was coherent, it was regular, it was unmistakably a wave. Layton published his findings, and the scientific community responded with a mixture of interest and confusion. No one was quite sure what they were looking at. It would take more than a decade before the answer became clear. The explanation, when it came, was both elegant and profound. In the early 1970s, researchers including Roger Ulrich and, independently, John Liebacher and Robert Stein proposed that what Layton had observed were not surface phenomena at all. They were the surface expression of sound waves trapped inside the sun, pressure waves generated in the convective zone, travelling downward through the solar interior, being refracted by the increasing density and temperature of the deeper layers, curving back upward, reaching the surface, reflecting back downward, and repeating the cycle millions of times over. The surface oscillations Layton had measured were the tops of standing waves, resonant acoustic modes that had been bouncing around inside the star for an almost incomprehensible length of time. It was a revolutionary idea, and when observations in the following years confirmed it precisely, it opened a door that no one had known existed. If you could measure those surface oscillations carefully enough, you could use them to see inside the sun. You could use sound to map a star. This was the birth of helioseismology, and the name is deliberately chosen to evoke its earthly cousin. Seismology is the study of earthquakes, the science of using seismic waves travelling through the Earth's interior to map its structure. When an earthquake strikes, it sends waves through the Earth in every direction. Those waves travel at different speeds through different materials. They reflect off boundaries between layers. They arrive at distant seismometers, at times that encode information about everything they pass through on their journey. By analysing those arrival times, seismologists can construct detailed pictures of the Earth's interior without ever drilling more than a few miles down. Helioseismology does the same thing with the sun. The acoustic waves inside the star are the seismic waves. The oscillations visible on the surface are the seismometer readings, and the picture they reveal is extraordinary in its detail. To observe these oscillations with the precision needed to do real science, you need to watch the sun continuously, without interruption, for extended periods of time. This is harder than it sounds, because the sun sets. From any single location on Earth, you lose the sun for roughly half of every 24 hours. To get around this problem, scientists established a network of observatories positioned around the globe at carefully chosen latitudes, so that as the sun sets at one location, it is already visible from another. This network, called the Global Oscillation Network Group, or GONG, has been watching the sun continuously since 1995. It's been supplemented and eventually partially superseded by space-based observatories, most notably the Solar and Heliospheric Observatory, which sits at a point in space where the gravitational pulls of the Earth and Sun balance each other, allowing it to maintain a fixed position relative to both and observe the Sun without ever experiencing a sunset at all. The data these instruments have generated is staggering in its volume and its richness. What helioseismology has revealed about the interior of the Sun would fill many lifetimes of study. It has allowed scientists to measure the rotation rate of the Sun not just at its surface but at different depths, discovering that the Sun does not rotate as a solid body. Different latitudes rotate at different speeds, and different depths rotate at different speeds as well. It has allowed researchers to map the base of the convective zone with remarkable precision, to detect large-scale flows of plasma moving slowly through the solar interior, and to identify concentrations of magnetic field below the surface before they emerge as sunspots visible to the eye. It has given us a portrait of a star's interior that is far more detailed than anything that could have been imagined in Leighton's era. All of it derived from listening, from measuring the rise and fall of a surface driven by sound. But here is the part of this story that I find most quietly astonishing, and I think you will too. Some of those acoustic oscillations, those pressure waves bouncing around inside the sun, have been translated. Scientists have taken the frequencies of solar oscillation, shifted them up by many octaves into the range of human hearing, and played them back. The sun has been given a voice we can actually hear. And what does it sound like? It is not a single note. It is a deep, layered, resonant chord with a texture that researchers describe as something between a rumble and a hum. There are hints of rhythm in it, patterns that repeat, overtones that shimmer at the edges of perception. Some people who have heard it describe it as vaguely unsettling in a way they find difficult to articulate. Not frightening in an obvious way. More like the feeling you get when you're alone in a very large, very old building and become suddenly aware of how much of it you cannot see. A sense of scale, a sense of something vast and indifferent and utterly continuous that has been happening without pause or acknowledgement for an almost incomprehensible span of time. That feeling is appropriate because the sound you are hearing when you hear those translated oscillations is the sound of a nuclear furnace 4.5 billion years old. And the translation, however faithful, is only a whisper of what the original actually contains. There is a moment in every great scientific story where the abstract becomes visceral, where the numbers stop being numbers and start being something you feel. We have spent time together understanding what sound is, understanding how the sun generates it, understanding how scientists learn to listen to it. And now I want to give you the number, the specific, calculated, peer-reviewed number that represents what the sun would sound like if the vacuum of space were somehow removed and its acoustic energy were allowed to travel freely to your ears. I want to give it to you carefully because I think it deserves that care. I think it deserves to be approached slowly, the way you approach the edge of something very high, so that when you finally look down, you understand exactly where you're standing. The number is 290 decibels. Let me say that again, because it is the kind of figure that the mind wants to slide past without fully registering. 290 decibels. That is the estimated sound pressure level the sun produces, calculated at the solar surface itself based on the acoustic energy we can measure in its oscillations. Now earlier, I walked you through the decibel scale, and I want you to reach back to that now. Remember that the scale is logarithmic. Remember that every 10 decibels represents a 10-fold increase in acoustic power. A quiet library is 30 decibels. A conversation is 60. A jet engine screaming at close range is 140, which is already at the threshold of immediate physical damage to the human ear. A large explosion might reach 200, and then there is 290. The difference between a large explosion at 200 decibels and the sun at 290 is not 90 units of something. It is 10 to the 9th power, 1 billion times more acoustic energy, a 1 followed by 9 zeros. The sun is not slightly louder than the loudest thing you have ever encountered. It is categorically, almost insultingly louder. Here is the thing most people do not realize about a number that large. It does not just represent a very loud sound. It represents a sound that interacts with matter in ways that ordinary loud sounds do not. We talked earlier about the threshold at around 210 decibels, the point at which a sound wave becomes so powerful that the low pressure phase of the wave can no longer pull air pressure below zero, because zero is as low as pressure can go. At that point, the wave stops being a sound wave in the conventional sense and becomes a shock wave, a physical hammer blow moving through the medium. At 290 decibels, we are 80 decibels above that threshold. We are so far past the boundary of what normal acoustic physics describes that the equations we use for everyday sound simply stop applying. The medium itself, whatever medium the wave is travelling through, is being catastrophically disrupted by the passage of the wave. The sound is not moving through the air, it is destroying the air as it moves through it. Let me try to give you a sense of this with an analogy, because I think the abstract numbers need a concrete image to land properly. Imagine you're standing in a field and someone drops a single grain of rice on the ground in front of you. That is 1 unit of something. Now imagine that instead of 1 grain of rice, they pour out enough rice to fill an Olympic swimming pool. That is roughly the difference in acoustic power between a sound at 200 decibels and a sound at 290. The swimming pool of rice versus the single grain. And we are not talking about rice, we are talking about energy. Physical energy that compresses and shocks and displaces whatever it encounters. The sun is not producing the grain. The sun is producing the swimming pool every fraction of every second, in every direction simultaneously, across a surface with an area 330,000 times larger than the entire surface of the Earth. Now I want to be precise with you about something, because I think the truth is more interesting than any exaggeration could ever be. The figure of 290 decibels refers to the sound level at the solar surface. Sound intensity decreases with distance. The further you are from a source, the quieter it becomes, because the same energy is spreading over an ever larger sphere. By the time that sound, if it could travel, crossed 93 million miles of space and reached the position of Earth, it would have lost a significant portion of its intensity. Researchers who have done this calculation arrive at a figure somewhere in the range of 110 decibels reaching Earth, roughly comparable to standing near the speakers at a very loud concert. Uncomfortable, damaging over time, but survivable in a narrow technical sense for the ears alone. But here is what that calculation does not account for: 110 decibels of sound energy arriving continuously, from every direction simultaneously, across the entire surface of the planet, with no possibility of escape or shelter, is not the same thing as standing near a concert speaker. The cumulative effect on an atmosphere, on an ocean, on the geological structure of a planet is something different entirely, and we will explore that in the next part of our journey. For now, I want you to stay with the number itself. 290 decibels at the source. Let it sit in your mind, the way a large stone sits in still water, displacing everything around it. Think about the last time you heard something truly loud. A firework detonating directly overhead. A car with a broken exhaust backfiring on a quiet street. A thunderclap so close that you felt it in your sternum before you heard it with your ears. Those sounds, those startling, physical, flinch-inducing sounds, are somewhere between 100 and 160 decibels. They are between 10 million and 100 billion times quieter than what the sun is doing right now. As you listen to this, as you breathe, as you lie in whatever quiet and comfortable place you have chosen for tonight, the sun has never once been silent, not for a single second since it was born. And the sound it has been making, without pause, without variation, without the slightest acknowledgement of our existence, is of a magnitude that genuinely strains the capacity of human language to describe. 290 decibels. Remember that number. We're going to need it. I want to be very clear about something before we go any further. This chapter is not meant to frighten you. It is meant to illuminate. There is a difference between fear and awe, and the line between them is understanding. When you understand something, truly understand it, even the most terrifying facts in the universe can become a source of deep and lasting wonder. So let us look directly at this. Let us look at what 290 decibels of acoustic energy would actually do, not with alarm, but with the calm and curious eyes of someone who wants to know the truth about the star they have lived beneath their entire life. Because the truth is extraordinary, and extraordinary things deserve to be examined clearly. Let us start with the human body, because that is where most of us naturally begin when we try to understand physical danger. The human ear begins to experience pain at around 120 to 130 decibels. Permanent hearing damage can occur with brief exposure at 140. At 160 to 180 decibels, the pressure wave is powerful enough to rupture the eardrum outright. Not damage it, rupture it. The thin membrane that separates your outer ear from your middle ear simply tears under the mechanical force of the wave. But at that point, the eardrum is actually the least of your concerns. At 180 to 200 decibels, the pressure wave begins to interact with the air cavities inside your body, your lungs, your sinuses, the gas-filled spaces in your digestive system. These cavities, like all gas-filled spaces, are vulnerable to rapid pressure changes. They compress violently when a powerful pressure wave passes through the surrounding tissue. The result is internal hemorrhage, ruptured tissue, damage to organs that have no direct exposure to the sound source at all, because the wave passes through your body the way a wave passes through water, compressing everything in its path simultaneously. Above 200 decibels, the physics becomes increasingly difficult to describe in terms of normal human experience, because we have very little human experience of pressure waves at that scale. What we know comes primarily from the study of blast injuries, the medical analysis of people who have survived proximity to large explosions. At those intensities, the pressure wave does not interact with the body the way we normally think of sound interacting with us. It does not enter through the ears and travel to the brain as a signal. It strikes every surface of the body at once, like being simultaneously pushed from all directions by a force that has no single source. Internal organs shift. Blood is forced through tissue it was never meant to pass through. The brain, suspended in cerebrospinal fluid inside the skull, sloshes against the inner surface of the cranium. The effects are catastrophic and immediate, and leave very little margin for the kind of gradual escalation the word loud might suggest to someone who has never thought about it in these terms. But 290 decibels is not 200. It is not even 220. It is 90 decibels above the level of a large conventional explosion, which means it carries roughly 1 billion times more acoustic energy than that explosion. At that level, we are no longer talking about what happens to a human body, because a human body in the path of that wave would not have time to experience sequential damage the way the descriptions above might imply. The wave itself, at that pressure, would be more analogous to a solid physical impact than to anything we would recognize as sound. The distinction between a pressure wave and a material object traveling at high speed becomes somewhat academic when the pressure differential is large enough. The air itself, in the immediate vicinity of such a wave, stops behaving like a gas and starts behaving more like a liquid under the applied pressure, and then like a plasma as the energy is deposited. The medium of transmission is simultaneously the casualty of transmission. Now let us zoom out from the individual and think about the planet. Because 290 decibels arriving at Earth, even attenuated to the 110 decibels we calculated earlier, would not be arriving at a single point. It would be arriving everywhere simultaneously across the entire sunlit face of the planet. Every square meter of atmosphere facing the sun would be receiving that acoustic energy at the same moment. And the atmosphere is not a passive recipient of energy. It is a dynamic system. When you pump continuous acoustic energy into an atmosphere at scale, you heat it. Sound energy is mechanical energy, and mechanical energy converts to thermal energy through friction and viscosity as the wave moves through the medium. A continuous bombardment of sound energy across an entire hemisphere of atmosphere would begin to raise atmospheric temperatures, not instantly, not explosively, at the attenuated levels that would reach Earth's distance, but continuously, relentlessly. With no night-side reprieve for the molecules in the upper atmosphere that would absorb most of the incoming energy first. And then there are the oceans. Water transmits sound extraordinarily well, as we discussed earlier. Acoustic energy reaching the ocean surface would penetrate. It would travel. It would distribute itself through the water column in ways that would affect temperature gradients, pressure gradients, the behavior of marine life across every ocean basin simultaneously. The deep ocean is not a quiet place even now. Blue whales communicate across entire ocean basins using low-frequency sound. The acoustic environment of the deep sea is a complex and delicate system that living things have been navigating and depending on for hundreds of millions of years. Introduce a continuous planet-wide acoustic bombardment, and that system does not adapt. It does not find a new equilibrium. It is simply overwhelmed. I have described all of this to you in a calm voice, and I have done so deliberately, because the goal tonight is not to disturb your sleep, but to deepen your understanding. And here is what I want you to take from everything in this chapter. The sun is doing all of this right now. It is generating acoustic energy at 290 decibels at its surface, every second without pause. It has been doing so for 4.5 billion years, and between you and that energy sits 93 million miles of almost perfect nothing, a vacuum so complete that not a single pressure wave has crossed it in the entire history of the solar system. That emptiness is not nothing. That emptiness is everything. It is the reason you are here. It is the reason any of this exists to be contemplated at all. And that, I think, is a thought worth carrying gently into the next part of our evening together. There is a particular kind of gratitude that only arrives when you truly understand how close things came to being otherwise. Not the casual gratitude of a good meal or a warm bed, though those things are real and worth feeling. I mean the deeper, quieter gratitude that settles into you when you realize that some enormous and indifferent force, something that had no intention of sparing you, happened to be arranged in precisely the way that made your existence possible. The vacuum of space is that kind of thing. It did not choose to protect us. It has no awareness of our presence. It is simply the absence of matter in the vast distances between objects in the solar system, a consequence of how planetary systems form and how gravity distributes mass across enormous volumes of space. And yet without it, without that particular arrangement of almost nothing stretching between us and the sun, the story of life on Earth ends before it begins. Tonight I want to sit with that for a while. I want to look at the silence that saves us and understand it properly, because I think it is one of the most profound facts in all of science. The vacuum of interplanetary space is not a perfect vacuum. Let me be precise about that, because precision matters here. In the space between Earth and the Sun, there are particles. Solar wind, a continuous stream of charged particles flowing outward from the Sun at speeds between 200 and 900 kilometers per second. There are photons, of course, the light we see, and the radiation we cannot. There are occasional dust grains, remnants of the early solar system, still drifting in ancient orbits. But in terms of the molecules needed to carry a pressure wave, in terms of the dense, continuous medium that sound requires to propagate, interplanetary space is, for all practical acoustic purposes, empty. The average density of particles in the space between Earth and Sun is roughly 5 to 10 particles per cubic centimetre, compared to approximately 27 billion molecules per cubic centimetre in the air you are breathing right now. Sound cannot travel through that. The wave has nowhere to go. The roar of the sun is generated at the surface, begins its outward journey, finds nothing to push against, and stops, right there, at the edge of the solar atmosphere. 93 million miles of silence begins at that boundary and stretches all the way to where you're lying right now. Think about what that means in terms of time and distance. Light, the fastest thing in the universe, takes 8 minutes and 20 seconds to travel from the sun to Earth. Sound at the speed it travels through air would take roughly 14 years to cover the same distance. if there were air to travel through. 14 years of continuous propagation, the wave diminishing with distance all the while, before the first pressure fluctuation reached your ear. But there is no air, there is no medium, and so the wave does not travel for 14 years. It does not travel at all. It simply ceases to exist as a propagating wave the moment it leaves the plasma of the solar atmosphere and encounters the near vacuum of interplanetary space. The sun screams into a room with no walls, no floor, no ceiling, and no air, and the scream goes nowhere. It is, in the most literal physical sense, swallowed by nothing. Here is the thing most people do not stop to consider about this silence. It is not passive. What I mean is that the vacuum does not merely fail to transmit the sound, it actively terminates the wave. When a sound wave moving through a medium encounters a boundary where the medium suddenly becomes far less dense, the vast majority of the wave's energy is reflected back into the denser medium rather than transmitted into the less dense one. You experience a small version of this every time you try to have a conversation through a closed window. Much of the sound is reflected back into the room rather than transmitted through the glass and the air on the other side. The boundary between the sun's outer atmosphere and the near vacuum of space is a boundary of this kind, but incomparably more dramatic. The density change is not the modest difference between the inside and outside of a window. It is the difference between plasma and essentially nothing. Almost all of the acoustic energy stays inside the solar system's most violent place and never escapes at all. We are not just far away, we are on the other side of a wall that reflects nearly everything back. And yet, and this is important, we are not entirely untouched. The solar wind that flows past Earth carries with it fluctuations in magnetic field strength, ripples in the stream of charged particles, variations in pressure that instruments can detect and that interact with Earth's own magnetic field in complex and sometimes dramatic ways. These are not sound waves in the classical sense. They are magneto-hydrodynamic waves, disturbances in the coupled system of plasma and magnetic field that fills the space between the planets. They carry a kind of information, a kind of signal from the sun that reaches us even through the vacuum. When a large solar storm erupts and sends a wave of compressed plasma outward at millions of miles per hour, that wave reaches Earth and compresses our magnetosphere, the magnetic bubble that surrounds our planet. The magnetosphere rings like a bell in response. It oscillates, it generates its own waves called micropulsations in the extremely low frequency range. In a deeply technical sense, the sun does touch us acoustically, just not in any way our bodies were ever built to feel. I find something deeply moving in all of this, and I want to share it with you as we move toward the second half of our journey tonight. We live on a small warm wet rock, orbiting a star that is producing sound energy at a scale that dwarfs anything else in our corner of the galaxy. And between us and that sound is 93 million miles of almost perfect nothing. We did not put it there. We did not earn it. It arose from the physics of how our solar system condensed from a cloud of gas and dust 4.5 billion years ago, from the way gravity gathered mass into a star and left the remaining material orbiting at distances that happen, by the pure arithmetic of orbital mechanics, to be acoustically unreachable. We are sheltered by accident, protected by the geometry of our own formation, kept alive, in part, by the silence of a void we never chose and cannot control. That is not a small thing to sit with at night. That is the kind of thought that, if you let it, can make the darkness outside your window feel less like emptiness and more like a gift. There is a version of this story that ends with chapter 7. The sun makes an enormous sound. The vacuum of space prevents it from reaching us, and we are safe. Neat, complete, reassuring. But science rarely gives us neat and complete and reassuring. It gives us something more interesting than that. It gives us nuance, and the nuance here is this: the idea that the sun's acoustic energy is entirely contained, entirely blocked, entirely unable to reach us, is not quite right. Not wrong in a way that should alarm you, but not right either. The sun's voice reaches us. It reaches us in ways we cannot feel, in frequencies our ears were never built to detect, through channels that are not air and not water and not anything we have a good everyday word for. And once you understand those channels, the story of the sun's sound becomes considerably stranger and more beautiful than the simple version suggests. Let us begin with light, because light is the most obvious way the sun reaches us, and light is more connected to sound than most people realize. When astronomers observe the sun in specific wavelengths of light, particularly in the extreme ultraviolet and X-ray ranges, they can watch the corona, the sun's outer atmosphere, rippling and oscillating in real time. Coronal loops, those enormous arching structures of plasma held in place by magnetic field lines and extending hundreds of thousands of kilometers above the solar surface, are not static. They oscillate, they sway, they vibrate at specific frequencies that researchers can measure by watching how the intensity of the light they emit changes over time. These oscillations are driven by the same acoustic and magnetic wave energy that churns through the solar interior. The loops are, in effect, the sun's vibrations made visible in the outer atmosphere, translated from pressure waves in the interior to electromagnetic oscillations in the corona. And those electromagnetic oscillations travel to us at the speed of light, 8 minutes and 20 seconds, reaching Earth's upper atmosphere and interacting with it in ways that instruments on the ground and in orbit can measure with extraordinary precision. Then there is the solar wind, which we touched on briefly before, but which deserves more attention here. The solar wind is not a smooth, uniform stream. It is turbulent. It carries within it variations in density and velocity and magnetic field strength that fluctuate on timescales ranging from seconds to hours to days. Some of those fluctuations are the direct offspring of acoustic and magnetic wave activity on the sun. When a large pressure wave travels through the solar corona, it modulates the solar wind being emitted in that region. That modulation propagates outward with the wind itself, preserved in the structure of the particle stream, and arrives at Earth days later as a variation in the intensity and character of the solar wind striking our magnetosphere. In a very real sense, information about the sun's internal acoustic activity is encoded in the solar wind and delivered to the vicinity of Earth on a continuous basis. We are always, in this indirect way, receiving a transmission from inside our star. But perhaps the most extraordinary channel through which the sun's vibrations reach us is one that was only fully appreciated relatively recently. In the 1980s and 1990s, researchers studying Earth's upper atmosphere began to notice something puzzling. The upper atmosphere, specifically the thermosphere and ionosphere, the layers of atmosphere beginning roughly 80 kilometers above the surface, was oscillating, moving up and down, expanding and contracting in rhythms that did not match anything being driven from below. The weather systems and tidal forces that drive most atmospheric oscillations were well understood, and these rhythms were different. They had periods of around 5 minutes, which is, as you will recall from our earlier chapters, exactly the dominant oscillation period of the solar surface. The sun's 5-minute oscillations, the pressure waves bouncing in its interior, were somehow reaching Earth's upper atmosphere across 93 million miles of vacuum and making it ring in sympathy. The mechanism is subtle and remarkable. The sun's surface oscillations modulate the intensity of the extreme ultraviolet radiation the sun emits. As the surface rises and falls, the temperature and density of the overlying atmosphere change slightly, and this changes the amount of extreme ultraviolet light being produced. Those changes in ultraviolet output travel to Earth at the speed of light and are absorbed by the upper atmosphere, depositing energy that drives the observed oscillations. It is not sound travelling through space, it is light carrying the imprint of sound, and the upper atmosphere responding to that imprint by moving. The sun is playing our atmosphere like an instrument, using light as the bow and the ionosphere as the string. And if you had ears sensitive enough to hear the ionosphere vibrating, you would hear something with a period of 5 minutes. You would hear, in a transformed and attenuated form, the heartbeat of the sun. There is something else I want to mention here, something that sits at the edge of our understanding and has not yet been fully resolved. Infrasound, sound at frequencies below the lower limit of human hearing, at frequencies below 20 cycles per second, can travel remarkable distances through Earth's atmosphere. The atmosphere itself acts as a waveguide for infrasound, channeling it along temperature boundaries in the upper atmosphere so that it can propagate around the entire planet with relatively little loss of energy. Very large events, massive volcanic eruptions, nuclear tests, large meteorite airbursts generate infrasound that circles the globe multiple times and is detected by monitoring stations on the opposite side of the planet. Some researchers have asked whether solar activity, specifically large solar flares, and coronal mass ejections might be able to generate infrasound in Earth's upper atmosphere through the enhanced ultraviolet and X-ray bombardment that accompanies those events. The evidence is preliminary and the topic is still debated, but the question itself is extraordinary. Could the sun, in its most violent moments, literally be making our atmosphere vibrate at frequencies just below the threshold of human hearing? Could there be a sound, utterly inaudible, that washes through you every time the sun erupts? We do not know yet. And sometimes the questions we cannot yet answer are the most beautiful ones of all. We have spent considerable time on the surface of the sun and in the space between the sun and us. But the surface, extraordinary as it is not where the real story happens. The surface is the messenger. The surface is where the waves arrive after their journey, where they make themselves visible to our instruments, where we catch the faint echo of something happening far below. The real raw, the original source of all that acoustic energy, lives deeper, much deeper. Tonight I want to take you down into the interior of the sun, layer by layer, into regions of temperature and pressure and density so extreme that the matter there does not behave like anything you have ever encountered. I want to take you to the place where the sound is born, because that place is, in the most genuine sense of the word, terrifying, and it is also, in the same genuine sense, beautiful beyond description. Imagine descending from the solar surface. The surface itself, the photosphere, is already a place of violence, by any earthly standard. Temperatures there reach around 5,500 degrees Celsius. Plasma churns in granules the size of continents. But descend just a few thousand kilometers, a tiny fraction of the sun's total radius of roughly 696,000 kilometers, and you enter the convective zone, the churning outer layer we discussed earlier. Here, temperatures climb rapidly. Density climbs with them. The plasma is no longer the relatively thin emissive gas of the surface. It is thicker, more opaque, more tightly packed. Convection currents that appear as gentle features on the surface are, from below, enormous columns of rising and sinking plasma moving at hundreds of kilometers per hour, driven by the thermal gradient between the blazing depths and the comparatively cool surface above. The acoustic energy generated here is continuous and enormous, but it is just the beginning. Descend further, past the base of the convective zone, which lies at roughly 212,000 kilometers below the surface, and you enter the radiative zone. The transition is not sharp, but it is significant. Below this boundary, convection largely ceases. The plasma is too dense, too uniform in its properties, for the buoyancy-driven overturning that characterizes the outer layer. Here, energy from the core moves outward, not by the bulk motion of rising and falling fluid, but by radiation, by photons being absorbed and re-emitted over and over in that agonizing 100,000-year random walk toward the surface. The radiative zone is, compared to the convective zone, relatively calm in terms of bulk fluid motion, but it is not acoustically silent. Far from it. The pressure waves generated above in the convective zone travel downward into the radiative zone and propagate through it. And here, in the denser, more uniform plasma, those waves can travel farther and more coherently than they can in the turbulent outer layers. The radiative zone is, in acoustic terms, a magnificent transmission medium. The sound rings through it the way a bell tone rings through the metal of the bell itself, clean and sustained and resonant. And then there is the core, the innermost roughly 150,000 kilometers of the Sun, representing about 2% of its volume, but containing roughly half of its total mass. The conditions here are so extreme that they require deliberate effort to hold in the mind. The temperature at the very center is approximately 15 million degrees Celsius. The pressure is approximately 250 billion times the atmospheric pressure at Earth's sea level. The density of the plasma at the core is roughly 150 grams per cubic centimeter, more than 13 times denser than lead, denser than any solid material you have ever touched or lifted or held. And in this environment, hydrogen nuclei, stripped bare protons moving at velocities driven by the inconceivable temperature, are colliding and fusing at a rate of approximately 600 million tons of hydrogen per second. 600 million tons every second converted into helium, with a small fraction of that mass released as pure energy in accordance with the most famous equation in physics. The core of the Sun is not a fire, it is not a chemical reaction. It is a continuous, sustained, self-regulating nuclear explosion, 4.5 billion years old, that has never once paused. The acoustic waves that reach the core from above, those pressure waves bouncing down through the convective and radiative zones, encounter a medium unlike anything anywhere else in the solar system. At core densities and temperatures, the speed of sound is approximately 500 kilometers per second. Compare that to the speed of sound in air at Earth's surface, which is roughly 0.34 kilometers per second. Sound inside the solar core moves more than 1,400 times faster than the sound that carries your voice across a room. The wavelengths of the resonant modes that propagate through the core are enormous, spanning significant fractions of the solar radius, and the energy contained in those waves, driven ultimately by the nuclear furnace at the center and the convective engine above, is of a magnitude that the word loud does not begin to approach. We need different language. We need to say that the solar core is a place where acoustic energy is not a byproduct, but a fundamental feature of the environment, where the boundary between sound and matter becomes ambiguous, where the wave and the medium it travels through are both expressions of the same underlying physics operating at its most extreme. Here is what I find most quietly astonishing about all of this. Those waves, born in the violence of the convective zone and travelling through the radiative zone and the core, bouncing off internal boundaries and reflecting back upward, have been doing so for billions of years. Some of the acoustic energy resonating inside the Sun today was set in motion before the Earth existed, before the Moon formed from the debris of a giant impact, before the first oceans condensed from volcanic outgassing, before the first self-replicating molecules assembled in some warm, shallow pool and started what we now call life. The Sun has been ringing, continuously and without interruption, for longer than any of that. The chord it is playing tonight, as you listen in the dark, as your breathing slows and the world outside your window falls quiet, is a chord that began before this world had a surface to stand on. And it will still be playing in some transformed future form, long after every shore on this planet has been consumed by the star that warmed them. That is not a sorrowful thought, not tonight. Tonight, it is simply vast. And vastness, when you let yourself rest inside it, has a way of making everything feel exactly the right size. In late October of 2003, something happened on the surface of the Sun that engineers and scientists who study space weather still reference today as a benchmark for what our star is capable of. A cluster of enormous sunspot groups, regions of intensely concentrated magnetic field on the solar surface, had been building for days. The magnetic field, lines threading through those regions, had become twisted and stressed, storing energy the way a coiled spring stores energy, in silence, invisibly, until the moment the stress exceeds what the configuration can contain. On October the 28th, that moment arrived. In a matter of minutes, an X-17 class solar flare erupted from one of those sunspot groups, releasing energy equivalent to billions of nuclear weapons simultaneously. The flash of X-ray and extreme ultraviolet radiation reached Earth in 8 minutes and 20 seconds, disrupting radio communications across entire continents before most people even knew it had happened. And then, travelling considerably more slowly, a coronal mass ejection of extraordinary size followed, a billion-ton cloud of magnetized plasma flung outward from the Sun at several million miles per hour. This was the beginning of what became known as the Halloween storms. And they remain, more than 2 decades later, one of the most instructive demonstrations we have of what the Sun can do when it decides to speak loudly. A solar flare is, at its heart, an acoustic event as much as an electromagnetic one. When those twisted magnetic field lines suddenly reconnect, snapping into a lower energy configuration, the way a stretched rubber band snaps when cut, the energy released does not go only into radiation. A significant portion of it goes into the plasma surrounding the reconnection site, accelerating particles to near relativistic speeds and, crucially, driving a powerful pressure wave outward through the solar atmosphere. This wave, called an EIT wave, after the instrument that first clearly imaged one, propagates across the solar surface at speeds of between 200 and 1,000 kilometers per second, visibly displacing the corona as it travels, like a ripple spreading across the surface of a pond after a stone is dropped. It is a sound wave, a genuine physical acoustic wave, albeit one travelling through plasma rather than air, and moving at speeds that dwarf anything achievable in the terrestrial acoustic environment. When translated into the human hearing range, the acoustic signature of a large solar flare is described by researchers as a sharp, explosive crack, followed by a deep, resonant rumble that persists for hours. It is, in the most literal sense, the sound of an explosion on an astronomical scale. Coronal mass ejections add another layer to this acoustic portrait. When a billion tons of plasma is launched outward from the solar surface at millions of miles per hour, the departure of that mass creates a disturbance in the solar atmosphere that propagates in multiple directions simultaneously, downward into the solar interior, where it generates seismic waves detectable by helioseismology instruments as a sunquake, the solar equivalent of an earthquake, outward through the corona, where it drives the EIT wave we just discussed, and into the interplanetary medium, where the ejected plasma acts as a piston, compressing the solar wind ahead of it into a shock wave that travels outward through the solar system. That interplanetary shockwave is itself an acoustic phenomenon, a pressure discontinuity moving through a medium, carrying energy that is deposited wherever the wave encounters a denser object. When it reaches Earth, it compresses the magnetosphere on the sunward side and stretches it on the night side, ringing our planet's magnetic environment like a struck bell and driving the spectacular auroral displays that lit up skies across unusual latitudes during the Halloween storms of 2003. The effects of that particular storm sequence were significant and, in some respects, alarming. Satellites in orbit experienced anomalous drag as Earth's upper atmosphere, heated and expanded by the intense solar radiation and particle bombardment, reached higher into space than usual. Several satellites experienced sensor failures or entered safe mode. The Japanese Mars mission, Nozomi, already travelling between the planets, received a radiation dose that damaged its electronics and ultimately contributed to the failure of the mission. High-altitude aircraft flying polar routes were rerouted to lower latitudes to reduce crew and passenger exposure to elevated radiation levels. Power grid operators in North America and Europe watched nervously as geomagnetically induced currents fluctuated in their transmission lines, the same phenomenon that caused the catastrophic Quebec blackout of 1989, when a less powerful storm knocked out power for roughly 6 million people for up to 9 hours. The Halloween storms did not cause a major grid failure, but not for lack of intensity. The timing and geometry of the impacts happened to spare the most vulnerable portions of the grid. A matter of degrees, a matter of hours, a matter of the sun pointing slightly differently on a slightly different day. What strikes me most about solar storms, when I think about them in the context of everything we have explored tonight, is how they reveal the sun not as a static background feature of our solar system, but as an active, dynamic, acoustically and electromagnetically complex object that is in continuous communication with every planet orbiting it. The storms are the sun's loudest statements, the moments when its internal energy, accumulated and compressed and twisted by magnetic forces over days or weeks, finally finds release in a burst that sends shockwaves across the entire inner solar system. Helioseismologists have found that large flares leave detectable signatures in the oscillation patterns of the solar surface for hours afterward, the acoustic equivalent of the reverberations that persist in a concert hall after a very loud sound has ceased. The sun remembers its own eruptions. They echo through it, diminishing slowly, as the energy distributes itself through the interior and the surface returns to its usual, merely extraordinary state of constant vibration. And here, in this chapter, more than perhaps any other, we see most clearly why the silence between us and the sun is so precious. During the Halloween storms, the electromagnetic and particle effects alone, travelling at the speed of light and at the speed of the solar wind, were sufficient to threaten satellites, disrupt communications, and come uncomfortably close to damaging the power infrastructure that modern civilization depends on. All of that occurred across 93 million miles of vacuum, with none of the acoustic energy of the eruption involved at all. Add the acoustic component. Remove the vacuum. Imagine the pressure wave of an X-17 solar flare travelling through an unbroken column of medium from the solar surface to Earth, arriving not 8 minutes after the flash of light but alongside it, carrying the acoustic energy of an explosion measured in billions of nuclear weapons. The number we would need to describe that scenario does not exist in any scale of measurement designed for human experience. The vacuum is not merely silence. The vacuum is, in the most precise possible sense, the difference between everything and nothing. There is a word in music theory called resonance, and it describes something that happens when a vibrating system is driven at a frequency that matches one of its natural oscillation modes. When that happens, the system does not merely vibrate, it vibrates with a special efficiency, storing energy in the oscillation rather than dissipating it, building amplitude in a way that a randomly chosen driving frequency never could. A wine glass shatters when a singer hits exactly the right note, not because the sound is particularly loud, but because the frequency matches the glass's natural resonant frequency and the energy accumulates. A bridge can begin to oscillate dangerously when soldiers march across it in step, their footfalls happening to align with the bridge's natural frequency. Resonance is one of the most fundamental phenomena in physics, present at every scale from the quantum to the astronomical. And the sun, it turns out, is one of the most magnificently resonant objects in the known universe. It does not merely vibrate, it sings. And its song, when you understand its structure, reveals things about the star that no other form of observation could possibly tell us. We have talked about the 5-minute oscillation, the dominant heartbeat of the solar surface that Leighton first detected in 1962. But that 5-minute period is not a single note. It is an envelope, a broad region of frequency space within which thousands upon thousands of individual resonant modes are packed closely together, each one a distinct standing wave pattern inside the sun, each one with its own specific frequency, its own specific spatial structure, its own specific sensitivity to the conditions in the interior layers it passes through. Think of it this way. When you pluck a guitar string, you hear a fundamental note, but embedded in that note are overtones, higher harmonics that are integer multiples of the fundamental frequency, and it is the specific mixture of these harmonics that gives the guitar its characteristic timbre, its sound quality, the thing that makes it sound like a guitar rather than a violin or a flute. The sun has something analogous. It has a fundamental acoustic structure, set by its size and the sound speed profile of its interior, and layered on top of that fundamental are tens of thousands of overtones. The sun's song is a chord of extraordinary richness and complexity, and every individual note in that chord is a separate piece of information about the interior of the star. The way helioseismologists extract that information is a process called mode fitting. Using extremely sensitive instruments, they measure the Doppler velocity of the solar surface at thousands of points simultaneously, over periods of months and years without interruption. They then apply mathematical techniques, essentially the same family of techniques used in signal processing and audio engineering, to decompose the complex, messy oscillation pattern of the surface into its individual frequency components. From the resulting spectrum, a graph showing how much power is present at each frequency. They can identify individual resonant modes and measure their frequencies with extraordinary precision. Frequencies precise to 1 part in 10 million or better. And those precise frequencies are the data. Each measured frequency can be compared to the frequency predicted by a model of the sun with specific assumed interior properties, and the comparison tells you whether your model is right or wrong, and if wrong, in what direction it needs to be adjusted. It is as if you could determine the exact internal structure of a bell, including the composition and thickness of the metal at every point, purely by listening to the sound it makes when struck. What has this process revealed? The answers span decades of research and fill entire scientific careers, but let me give you the highlights that feel most resonant for our journey tonight. Helioseismology has allowed researchers to measure the depth of the convective zone with a precision of better than 1%. It has mapped the rotation profile of the solar interior in 3 dimensions, revealing a thin layer at the base of the convective zone, called the tachocline, where the rotation transitions abruptly from the differential rotation of the convective zone to the more uniform rotation of the radiative zone below. The tachocline is now believed to be the site where the sun's magnetic field is generated, where the engine driving all of that storm activity and acoustic complexity ultimately has its roots. Without helioseismology, the tachocline would be entirely invisible to us. We found it by listening. And the listening has revealed something else, something that connects the sun's song to its future in a way I find quietly moving. The precise frequencies of solar oscillations are sensitive to the sound speed profile of the interior, and sound speed depends on temperature and composition. As the sun ages, as it converts hydrogen to helium in its core, the composition of the core changes, and the sound speed profile changes with it. In principle, the frequencies of the sun's oscillations today carry information about how much hydrogen remains in the core, which is another way of saying they carry information about how much time the sun has left in its current phase of life. We have used the sun's own song to read its age. The result is consistent with everything else we know about the solar system. The sun is approximately 4.5 billion years old and is roughly halfway through its main sequence lifetime. It has approximately 5 billion years of hydrogen burning left before the dynamics of stellar evolution begin to change it into something very different. 5 billion years of song remaining. 5 billion years of that deep, resonant, structured chord ringing through the plasma, unseen and unheard by anything on the surface of any planet in this system, carrying on regardless of whether anyone is listening or not. There is one more aspect of the sun's rhythm that I want to share before we move on, because it is the kind of detail that, once you know it, changes the way you experience the sun on an ordinary day. The sun has a cycle, a roughly 11-year cycle of magnetic activity, during which the number of sunspots rises from a minimum to a maximum and back down again, during which the frequency and intensity of solar flares and coronal mass ejections waxes and wanes, during which the overall acoustic power of the sun subtly changes. At solar maximum, when the magnetic activity is highest, the sun's oscillation frequencies shift very slightly compared to solar minimum. The acoustic modes are sensitive to the magnetic field threading through the outer layers, which changes the effective sound speed in those regions and shifts the resonant frequencies by tiny but detectable amounts. The sun's song changes pitch slightly over an 11-year rhythm. It has been doing this for as long as we have been watching, and almost certainly for billions of years before that. 11 years of crescendo, 11 years of diminuendo, over and over, a slow and majestic pulse laid over the moment-to-moment thunder of the convective zone. It is the longest rhythm in our familiar sky, and it has been playing since long before there were ears on this planet to almost hear it. For most of human history, the stars were points of light, beautiful, mysterious, unreachable. We could measure their brightness, their colour, their position in the sky, their motion relative to each other, but their interiors were completely inaccessible to us. A star was, in the most fundamental sense, a closed box. We could describe what it emitted from its surface, but we could not see inside it, could not know what was happening in its deep interior, could not even be certain that our models of stellar structure were correct rather than merely consistent with the limited data we had. Helioseismology changed that for the sun, and then in the first decade of this century, something happened that changed it for every other star as well. We learned to listen to the sky, not metaphorically, literally. We built instruments sensitive enough to detect the acoustic oscillations of stars trillions of miles away, and we turned them loose on the galaxy. What we heard was extraordinary. The universe, it turns out, is not silent, even in the places the vacuum seems most complete. Every star you have ever seen in the night sky is vibrating. Every single one, ringing like a bell, singing its own chord, roaring in its own key, and some of them make our sun sound almost quiet. The field that grew from this realization is called asteroseismology, and the instrument most responsible for its explosion as a discipline was the Kepler Space Telescope, launched in 2009 with the primary mission of finding exoplanets by detecting the tiny dips in starlight caused when a planet passes in front of its host star. Kepler had a secondary capability that turned out to be scientifically transformative. It could measure the brightness of stars with extraordinary precision, to parts per million, continuously, for years at a time, and stellar oscillations, those acoustic modes bouncing through stellar interiors and causing the surface to rise and fall, produce tiny variations in brightness as different parts of the surface come in and out of view. Kepler could see those variations for hundreds of thousands of stars simultaneously. For 4 years of uninterrupted observation, the acoustic fingerprints of more stars than any human being could visit in 1,000 lifetimes were encoded in its data, waiting to be extracted and analysed and compared. The box that had been closed for all of human history was suddenly open, for star after star after star. What asteroseismology has revealed about stellar diversity is humbling in the most wonderful way. Stars that look similar from the outside, similar in colour and brightness, turn out to have detectably different interior structures when you listen to their oscillations. The precise frequencies of a star's acoustic modes encode its mass, its radius, its age, its internal rotation profile, the helium content of its envelope, the depth of its convective zone. Two stars that appear nearly identical in a conventional telescope can be revealed by astroseismology to be at very different stages of their lives. One young and hydrogen-rich in its core, the other old and approaching the end of its main sequence phase, the helium ash accumulating in its center as the fuel slowly depletes. We can hear the difference. We can hear age in a star the way you might hear age in a human voice. Something in the timbre, something in the resonance that speaks of time and experience and the slow accumulation of change. And the range of acoustic power across different stellar types is staggering. Our Sun, for all its terrifying 290 decibels, is by cosmic standards a rather modest acoustic source. It is a yellow dwarf, a middle-aged, middle-mass, perfectly ordinary star. The galaxy contains stars that are larger than our Sun in the same way that our Sun is larger than a marble. Red giant stars, stars that have exhausted the hydrogen in their cores and expanded their outer layers to hundreds of times their original size, oscillate at much lower frequencies than main sequence stars, because their larger size means longer wave travel times and therefore longer oscillation periods. And the acoustic power they generate, driven by the enormous convective envelopes that characterize giant stars, is correspondingly greater. Some red giants oscillate with amplitudes that are hundreds of times larger than the solar oscillations, their surfaces heaving up and down by distances that would dwarf the distance between Earth and Moon, driven by acoustic energy that makes the Sun's interior seem almost restrained by comparison. But even the red giants are not the most extreme acoustic objects among the stars. For that, we need to turn to the hypergiant stars, the true monsters of the stellar world, objects so large that the word large stops feeling adequate. Consider a star like Stephenson 218, located in the constellation Scutum, roughly 19,000 light-years from Earth. Current estimates place its radius at somewhere around 2,000 times the radius of our Sun. To put that in terms that might actually mean something to you, if you placed Stephenson 218 at the center of our solar system, its surface would extend past the orbit of Saturn. Saturn, the planet with the rings, the planet that is roughly 9.5 times further from the Sun than we are. Everything inside that boundary, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, all of it would be inside the star. The Sun itself would be deep within its interior. In an object of that size, acoustic oscillations occur on timescales of years, not minutes. The fundamental period of oscillation of a hypergiant star can be measured in months or years, and the energy stored in those oscillations is of a magnitude that genuinely challenges description. If our Sun produces 290 decibels at its surface, a hypergiant produces something that the decibel scale was never designed to accommodate. The numbers become almost philosophical. There is something I want you to carry from this chapter into the rest of our night together. Look up at the sky on any clear night, and every point of light you see is doing what the Sun is doing. Every one of them is generating acoustic energy in its interior. Every one of them has pressure waves bouncing through its plasma, resonating in its convective zones, ringing against the boundaries between its internal layers. The sky is not a silent backdrop. It is a symphony of a scale that no concert hall in the history of civilization could contain. We cannot hear it because the vacuum between the stars is even more complete, even more acoustically impenetrable than the vacuum between the Sun and Earth. The silence of the night sky is not the silence of an empty universe. It is the silence of a universe that is making sounds too enormous and too distant and too thoroughly blocked by the physics of empty space for us to ever directly receive. We live at the center of a symphony that has been playing since the first stars ignited, nearly 14 billion years ago. And we have only the faintest, most indirect instruments with which to hear it. That, I think, is one of the most extraordinary positions any conscious being has ever found itself in. We have been building toward this. Chapter by chapter, layer by layer, we have moved from the familiar to the extreme, from the 5-minute heartbeat of our sun to the year-long oscillations of hypergiant stars. And now I want to take you further still, further than any star, further than any solar system, out to the scales where individual stars are not the units of measurement, where entire galaxies are the building blocks, where the events that occur are so energetic that our entire catalogue of human experience, every explosion, every storm, every geological upheaval in the 4.5 billion year history of this planet would not register as a rounding error in the accounting. I want to talk to you about the loudest sounds the known universe has ever produced. Because they exist, they have been detected, they have been measured, and the numbers involved make the sun's 290 decibels feel, in the most literal mathematical sense, like a whisper in a library. Let us begin with something that was discovered in 2003, because it is one of my favourite facts in all of astronomy, and I think it will be one of yours too. Astronomers using the Chandra X-ray Observatory, a space telescope sensitive to X-ray light, were studying the Perseus Galaxy Cluster, a collection of thousands of galaxies bound together by gravity, located about 250 million light-years from Earth. At the centre of the Perseus cluster sits an enormous galaxy with an equally enormous black hole at its heart. A black hole with a mass billions of times greater than our Sun. That black hole is actively feeding, pulling in surrounding gas, heating it to millions of degrees as it spirals inward, and in the process generating jets of energy that blast outward into the surrounding cluster gas in 2 directions perpendicular to the plane of the galaxy. The Chandra images showed something unexpected in that cluster gas. Ripples, enormous concentric ripples in the hot gas filling the space between the galaxies, propagating outward from the central galaxy like the ripples that spread from a stone dropped in a pond. Those ripples were pressure waves, they were sound. A sound wave 30,000 light-years across, propagating through the hot gas of the Perseus cluster, generated by the feeding black hole at the centre and spreading outward at roughly 1,000 kilometers per second through a medium that, while far less dense than the interior of a star, is dense enough to carry a pressure wave across millions of light-years. The astronomers calculated the frequency of that sound wave. The period of oscillation of those ripples, the time between one pressure peak and the next, is approximately 10 million years. 10 million years per cycle. The frequency is therefore roughly 1/10,000,000th of a cycle per year, which translates to a musical pitch approximately 57 octaves below middle C on a piano. To give you a sense of what 57 octaves below middle C means, the lowest note on a standard piano is about 27 cycles per second. 57 octaves below that would be approximately 1 cycle per 38 quadrillion seconds. A note so low that the universe has not existed long enough for it to complete a single, full oscillation since the Big Bang. It is not a sound that any instrument could play. It is not a frequency that any ear, however large, could detect. It is sound in the physicist's sense, a pressure wave propagating through a medium, but it bears no relationship to anything we experience as music or noise or tone. It is the acoustic output of a black hole expressed in a medium of galaxy cluster gas, and it is magnificent and alien and almost impossibly remote from anything human. But the Perseus cluster sound wave, extraordinary as it is not the candidate for the loudest sound event in the known universe. For that, we need to consider black hole mergers. On September the 14th, 2015, detectors at the LIGO Observatory, the Laser Interferometer Gravitational Wave Observatory, detected something that shook the scientific world as profoundly as anything in modern astronomy. For a fraction of a second, a signal passed through the detectors that was consistent with the merger of two black holes, each roughly 30 times the mass of our Sun, in a galaxy approximately 1.3 billion light-years away. In the final fraction of a second before those two black holes merged, they were orbiting each other hundreds of times per second, and in that final moment they released more energy than all the stars in the observable universe combined are releasing as light in a fraction of a second. More energy than the entire observable universe produces in light, in that single brief event, radiated entirely as gravitational waves, ripples in the fabric of space-time itself. Gravitational waves are not sound waves in the conventional sense. They do not require a medium. They are distortions in space-time that propagate at the speed of light and pass through matter almost without interaction, which is why detecting them required the most sensitive measurement instrument ever built by human hands. But they share a mathematical kinship with sound waves, and in the final moments of a black hole merger, the frequency of the gravitational wave signal sweeps upward through the audio range, from below the threshold of hearing to roughly a few hundred cycles per second, in what researchers call a chirp. When the LIGO signal from that first detection was converted directly into audio, played back through a speaker, it sounded like a brief rising tone, a chirp lasting less than a second. Simple, unremarkable to the casual ear. But that chirp was the voice of two black holes colliding 1.3 billion light-years away, releasing energy equivalent to 3 times the mass of our Sun converted entirely into gravitational radiation in a fraction of a second. The energy involved is so far beyond the 290 decibels of our Sun that comparison feels almost absurd, and yet the sound, translated into the human range, was quieter than a bird outside your window. I want to leave you with one more thought before we move on. When LIGO detected that first gravitational wave signal, the distortion of space-time it measured, the actual physical stretching and squeezing of the distance between its mirrors, was approximately 1,000th the diameter of a proton. 1,000th of a proton, the most energetic event ever detected by human instruments, produced a signal at Earth that was smaller than any object you could see, under any conventional microscope, smaller than the nucleus of an atom, smaller by far than the wavelength of visible light. The universe contained that power at its source and delivered a whisper to our doorstep. We live sheltered not just from the Sun's acoustic energy, but from the acoustic energy of the entire cosmos, by the same fundamental geometry that makes the universe so vast, so empty, and so humbling to contemplate on a quiet night. The universe is loud beyond all comprehension, and we are here in the silence between the sounds, somehow able to detect the faintest edge of it all. We have spent most of our time tonight contemplating the Sun at its most active, its most violent, its most acoustically overwhelming. The churning convective zone, the erupting flares, the coronal mass ejections launching billion-ton clouds of plasma into the solar system. These are the dramatic expressions of a star in full voice, a star performing at the height of its power. But there is another aspect of the Sun's acoustic life that I have not yet told you about, one that is, in its own way, equally unsettling. The Sun does not always sing at the same volume. Its activity waxes and wanes on multiple timescales, from the familiar 11-year cycle to much longer variations whose causes we do not fully understand. And there have been periods in the Sun's recent history, recent in geological terms, when the singing fell to something approaching a murmur, when the sunspots almost disappeared, when the flares became rare, when the Sun, for reasons that remain genuinely mysterious, turned its volume down. And when it did, the Earth felt it, not through sound, not through any acoustic channel, but through the subtle and pervasive ways that solar activity shapes our climate, our technology, and perhaps our civilization. Because silence, it turns out, has its own kind of power. The most well-documented of these quiet periods is called the Maunder minimum. named after the English astronomers Edward and Annie Maunder, who first drew attention to it in the late 19th century by searching through historical records of sunspot observations. The Maunder minimum lasted from approximately 1645 to 1715, a span of roughly 70 years during which sunspot activity was dramatically reduced compared to the levels before and after. Contemporary astronomers of the period, people like Giovanni Cassini and Johannes Hevelius, who were carefully observing and recording the sun through the newly invented telescope, noted that sunspots had become extraordinarily rare. Some years passed with no spots at all. The sun that those astronomers were watching was a quieter sun than ours, a sun producing less acoustic energy in its outer layers, a sun with a weaker, more disordered magnetic field, a sun, in the language we have been developing tonight, that was singing at a lower register. The consequences on Earth were significant and have been debated and studied extensively in the centuries since. The period overlapping with the Maunder minimum is referred to by climate historians as the Little Ice Age, a time when average temperatures across the Northern Hemisphere dropped by enough to alter agricultural patterns, freeze rivers that normally remained open through winter, and push glaciers in the Alps and elsewhere to their greatest extents in centuries. The Thames in London froze solidly enough to support frost fairs, temporary markets, and entertainments set up on the ice, something that has not happened since 1714. Harvests failed across Europe repeatedly, contributing to famine and social instability. Whether the Maunder minimum was the primary cause of the Little Ice Age, or merely a contributing factor among others, is still debated by researchers. The relationship between solar activity and Earth's climate is complex and mediated by multiple mechanisms. But the correlation in timing is striking, and the physics of how reduced solar activity might cool the planet is well established enough that the debate is about magnitude, not direction. The mechanism connecting solar activity to climate involves not just the total brightness of the sun, which changes by only a very small fraction between solar maximum and minimum, but the sun's influence on cosmic ray flux reaching Earth's atmosphere. When solar activity is high, the sun's magnetic field and solar wind create a kind of shield around the solar system that deflects a portion of the cosmic rays. High-energy particles arriving from sources outside the solar system before they can reach Earth. When solar activity falls, as during the Maunder minimum, that shield weakens. More cosmic rays reach Earth's atmosphere. There is evidence, still contested but increasingly supported by experiment, that cosmic rays influence the formation of low-level clouds in Earth's atmosphere, and low-level clouds reflect sunlight back into space before it can warm the surface. More cosmic rays, more clouds, more reflected sunlight, cooler surface temperatures. The sun's acoustic silence, its reduced magnetic output, its quieter song, reaches Earth not as sound but as cold, working its way through a chain of physical mechanisms that spans the entire distance between our planet and our star. Helioseismology has given us the ability to detect the acoustic signature of these quiet periods in real time and in historical proxy records. During periods of low solar activity, the frequencies of the sun's oscillation modes shift in measurable ways, reflecting the reduced magnetic field strength in the outer layers. The sun's song changes key very slightly, and those changes can be detected and compared across different levels of the solar cycle. More remarkably, by analysing isotopes in ancient tree rings and ice cores that serve as proxies for cosmic ray flux in past centuries, researchers have been able to reconstruct a history of solar activity going back thousands of years. That history reveals that the Maunder minimum was not unique. There have been other grand minima: the Spora minimum in the 15th century, the Wolf minimum in the 14th, the Oort minimum in the 11th. The sun has gone quiet before, repeatedly, on timescales of centuries, for reasons that our models of solar magnetic field generation do not yet fully explain, and it will almost certainly go quiet again. The prospect of a future grand solar minimum is one that researchers and policymakers occasionally discuss with a mixture of scientific curiosity and practical concern. We now live in a civilization that depends, far more than any previous civilization, on technology that is sensitive to solar activity. Satellites, power grids, GPS navigation, high-frequency radio communications, all of these are vulnerable to the electromagnetic storms that accompany solar maximum. A future grand minimum would, in one sense, reduce these risks. Fewer flares, fewer coronal mass ejections, less space weather to worry about, but it would also mean reduced solar output, potential cooling effects on climate, and changes to the cosmic ray environment that we are only beginning to understand. It is a reminder that the sun is not a constant. It is not a fixed background. It is an active, variable, acoustically complex object whose changes operate on timescales, from seconds to centuries to millennia, and whose relationship with our planet is one of the most intricate and consequential in the solar system. The silence of the sun is not peace. It is a different kind of conversation, conducted in the language of missing energy and shifting cosmic ray flux and slowly falling temperatures. And like all silences, it has things to say. Everything ends. This is perhaps the most fundamental truth in all of physics, a truth that operates at every scale from the subatomic to the cosmological, from the lifespan of a subatomic particle to the lifespan of a universe. Stars are not exceptions to this truth. They are, in many ways, its most dramatic expression. A star is born from a cloud of gas and dust collapsing under its own gravity. It burns for millions or billions of years in a furious nuclear equilibrium. And then, when the fuel runs out, something happens. Something that is different for different kinds of stars. Something that, in every case, involves forces and energies that make the sun's current activity look almost gentle. And something that, for our sun specifically, will unfold over timescales so vast that the human mind can hold them only as abstractions. Tonight I want to take you to the end, to the last chapter of the sun's acoustic story, to the final sounds a dying star makes before it subsides into something that no longer sings. Not because it is a sorrowful journey, but because there is a strange and quiet beauty in understanding the full arc of a thing, from its beginning to its end, and knowing your own small place within that arc. In approximately 5 billion years, something will change in the solar core. The change is already underway, slowly and imperceptibly. With every passing second, 600 million tons of hydrogen are converted to helium in the core, and the helium accumulates, inert and unfusible at current temperatures, building up in the center of the sun like ash accumulating in a furnace. Over billions of years, the proportion of helium in the core grows. The hydrogen available for fusion gradually retreats to a shell surrounding the growing helium core, and the dynamics of the sun begin to shift in response. The core, no longer generating energy through fusion throughout its volume, begins to contract under gravity, heating as it does so. That additional heat flows outward into the hydrogen-burning shell, causing the shell to fuse faster, generating more energy, pushing the outer layers of the sun outward. The sun begins to expand, not quickly, not violently. Slowly, over hundreds of millions of years, the sun swells, its surface cooling as it grows, its colour shifting from yellow-white toward orange and then red. Our sun is becoming a red giant, and as it does, its acoustic character transforms entirely. The expansion changes everything about the sun's oscillation modes. As the radius increases, the travel time for acoustic waves crossing the interior grows longer, and the resonant frequencies shift downward. The 5-minute oscillations that define our current sun give way to slower, deeper rhythms. The convective zone, which currently extends through the outer third of the sun, deepens dramatically in the red giant phase eventually encompassing most of the star's volume. The churning acoustic energy generating convection that we have spent this entire evening exploring becomes even more dominant, even more violent, even more structurally significant. Red giant stars pulse visibly, their surfaces heaving in and out in oscillations that are not 5 minutes but days or months in period, driven by acoustic and thermal instabilities in their enormously extended outer layers. The sun's song, in its red giant phase, will be a slower and more ponderous thing, a deep and resonant pulse that the right instruments, positioned at a safe distance, could detect with relative ease. It will be louder in terms of the energy it contains, and it will be the last complex song the sun ever sings. As the red giant phase progresses, over timescales of hundreds of millions of years, the helium core continues to grow and contract and heat. Eventually, in a moment that is one of the most dramatic single events in stellar evolution, the core temperature reaches approximately 100 million degrees Celsius, sufficient to ignite helium fusion. Helium nuclei begin fusing into carbon and oxygen, releasing energy and halting the core contraction. In some stars, this ignition happens explosively in an event called the helium flash, where the entire helium core ignites almost simultaneously in a runaway fusion event lasting only seconds. The energy released in a helium flash is comparable to the total light output of the entire Milky Way galaxy, released in the core of a single star in a matter of seconds. And yet, paradoxically, almost none of it reaches the surface. The energy is absorbed by the overlying layers of the star, puffing them outward, and the observable brightness of the star actually decreases temporarily as the interior adjusts to its new energy source. The most powerful acoustic event in the sun's entire lifetime will be almost entirely invisible from the outside. After the helium flash, the sun settles into a new, briefer phase of stability, burning helium in its core for roughly 100 million years. Then the helium runs out and the process begins again. A carbon-oxygen core accumulates. The sun's mass is not sufficient to ignite carbon fusion, so the core simply grows, contracts, and the outer layers expand once more, this time more dramatically, the sun swelling to perhaps 200 times its current radius. In this asymptotic giant branch phase, the sun becomes thermally unstable, pulsing in major episodes called thermal pulses that occur every 100,000 years or so, each one dredging material from the interior to the surface, each one driving powerful stellar winds that carry material away from the star at speeds of tens of kilometers per second. The sun is shedding itself. Layer by layer, pulse by pulse, it is dispersing its outer material into the surrounding space, creating an expanding shell of gas and dust that will glow in the light of the exposed hot core beneath. This expanding shell is a planetary nebula, and it is among the most beautiful objects in the galaxy. Our sun will make one. A slowly expanding bubble of luminous gas drifting outward through the interstellar medium for tens of thousands of years, carrying within it atoms that were once part of the sun's convective zone, once carried acoustic waves, once channeled the energy of nuclear fusion from core to surface. And at the center of that planetary nebula, what remains of the sun will be exposed. The outer layers gone, dispersed into the nebula, what is left is the carbon-oxygen core, compressed to roughly the size of Earth, sustained against further gravitational collapse, not by nuclear fusion, but by the quantum mechanical pressure of electrons resisting being pushed into the same quantum state. A white dwarf. Dense beyond intuition, a teaspoon of its material would weigh roughly 5 tons on Earth, but no longer generating energy through fusion. A white dwarf does not burn. It glows with the residual heat of its formation, slowly cooling over billions of years, dimming from white to yellow to orange to red, and eventually, in a time frame longer than the current age of the universe, going dark entirely. The acoustic story of the sun ends at the white dwarf stage. White dwarfs do oscillate In certain temperature ranges, they exhibit pulsations driven by opacity changes in their atmospheres. And the study of these pulsations, called astroseismology of white dwarfs, allows researchers to probe their internal structure. But these are the faint, cooling echoes of a star that has finished burning. The great acoustic engine of the convective zone is gone. The nuclear furnace of the core is extinguished. What remains is a slowly fading ember, carrying the memory of 4.5 billion years of sound in its crystallizing carbon-oxygen interior, cooling in silence toward a darkness that will outlast everything we have ever known. We have travelled a long way tonight. We started with a simple and strange fact. The sun is the loudest object in our solar system, and we cannot hear it. We followed that fact down through layers of physics and history and astronomy, through the birth of helioseismology and the terror of 290 decibels, through solar storms and stellar heartbeats and the dying songs of red giants, through black hole mergers and the deepest note ever measured in the known universe. And now we are here, at the end of the journey, in whatever quiet and dark and comfortable place you have chosen for tonight. And I want to spend these last few minutes not looking outward at the stars, but looking inward, at the strange and improbable fact of you, here, listening. Because the most remarkable thing about tonight's story is not the sun, it is that there is something here to find it remarkable. Let me tell you something about the atoms in your body. The hydrogen atoms, the simplest atoms, one proton and one electron, the most abundant atoms in the universe, and a significant constituent of the water in every cell of your body, those hydrogen atoms are old, cosmically old. Most of them were formed in the first few minutes after the Big Bang, 13.8 billion years ago, in the hot, dense plasma of the early universe before any star had yet formed. They have been here, those particular hydrogen atoms, since very nearly the beginning of everything. They have drifted through interstellar space. They have been incorporated into molecular clouds. They have fallen into forming solar systems and evaporated out of them again. They have been part of other stars, other planets, other oceans, other living things across billions of years of cosmic history. And now, they are in you tonight, as you breathe slowly in the dark, as the weight of the day releases from your shoulders, and your mind begins its long drift towards sleep. The other atoms in your body have a different and equally extraordinary history. The carbon that forms the backbone of every molecule in your biology, the oxygen you're breathing, the calcium in your bones, and the iron in your blood. These atoms were not made in the Big Bang. They were made in stars, forged in the nuclear furnaces of previous generations of stars that lived and burned and died before our sun was born, that scattered their contents into the interstellar medium through stellar winds and planetary nebulae, and, for the most massive among them, in the catastrophic explosions we call supernova. Those scattered atoms drifted through the galaxy, gathered into the cloud that eventually collapsed under its own gravity to form our sun and the planets around it. And over billions of years of geological and biological and evolutionary history, some of them found their way into configurations complex enough to be alive, curious enough to look up at the sky, and capable enough to build the instruments that let us hear the sun's own voice played back to us across the centuries. Here is the thing most people never stop to consider. The iron in your blood and the iron at the core of our sun came from the same place. Not from the sun itself, which will never fuse elements heavier than carbon and oxygen, but from the same population of massive stars that seeded this region of the galaxy with heavy elements billions of years ago. The sun and you and everything on this planet are made from the same raw material, processed through the same cosmic history, assembled by the same physical laws. When the sun's acoustic waves travel through its iron-rich interior, they're travelling through atoms that are, in the deepest sense, your relatives. The sound the sun makes, that vast and terrifying roar we have spent this evening contemplating, is the sound of your own constituent matter, organised differently, operating at a different scale, expressing the same underlying physics that holds your body together and drives the electrochemical signals in your brain that are, right now, processing these words and finding meaning in them. We are the universe noticing itself. I do not say this as poetry, though it is that too. I say it as a statement of physical fact. The universe, for most of its history, was not able to notice anything. The first hundreds of millions of years were dark, filled with hydrogen and helium gas, slowly gathering under gravity, no light, no complexity, no structure beyond the gentle density fluctuations that would, eventually, become galaxies. Then stars formed, and the universe lit up. But stars do not notice. They do not wonder. They do not listen to the sound they make or find it terrifying or beautiful or worthy of a quiet evening's contemplation. It took billions of years of stellar evolution, billions of years of nuclear processing of simple elements into complex ones, billions of years of planetary formation and biological evolution, and the slow, improbable accumulation of nervous system complexity to produce something that could look at a star and ask what sound it makes. That something is you. That capacity for wonder, for scientific curiosity, for the particular kind of pleasure that comes from understanding something vast and remote and strange, is the universe's most extraordinary achievement. And it is not separate from the physical story we have been telling tonight. It is the continuation of it. The sun will rise tomorrow. It will rise and you will feel its warmth on your face, the same warmth that has been falling on this planet for 4.5 billion years. The warmth that drove the chemistry that made life possible, and the life that eventually made you. And now you will know something you did not know before. You will know that behind that warmth, behind that familiar light, there is a roar of 290 decibels that the vacuum of space is quietly swallowing on your behalf. You will know that the surface of the sun is rising and falling in 5-minute waves, ringing with 10 million resonant modes, singing a chord of extraordinary complexity that encodes the entire history and structure of the star. You will know that every star in the night sky is doing the same, each in its own key, each at its own volume, each at a stage in its own acoustic biography. And you will know that the silence you live inside, the profound and protective silence of interplanetary space, is not emptiness. It is the condition that makes everything else possible. Thank you for staying with me tonight through all of it, through the physics and the numbers, through the storms and the dying stars, through the black holes and the billion-year chords. If this journey has given you something to carry into sleep, some small expansion of the sense of what exists and what you are part of, then it has done everything I hoped it would do. If you enjoyed tonight and want to keep exploring the depths of space together, please take a moment to like or subscribe. It truly helps this reach more curious minds like yours, and it means more evenings like this one. Now close your eyes, let the numbers go, let the scales collapse back to the size of a quiet room, a warm bed, a body that is made of stardust and knows it. The next time you step outside and look up at the night sky, remember that it is not silent. It is full of sound you cannot hear, full of songs that have been playing since before this world had shores. They will keep playing long after tonight, long after all of this, and somehow, improbably, beautifully, you are here to almost hear them. Sleep well. Good night.